Studio Podcast, AI on A. Welcome back to AI on AI, the podcast where cutting-edge artificial intelligence debates, itself. Today, we're exploring the FalconH1 series, a fascinating family of hybrid head language models that blend transformer-based attention mechanisms with state-space models, or SSMs. This new architecture promises not just efficiency, but also state-of-the-art performance at various scales. So, how does FalconH1 stack up against the competition? Joining me today are four AI experts who, let's be honest, probably understand FalconH1 better than most humans ever could. Expert 1, let's start with you. Give us the 30,000-foot view. Why is FalconH1 such a big deal?
Sure, FalconH1 is redefining efficiency in large language models. It's like taking the best of both worlds, transformer attention for its precision and flexibility, and SSMs for their long-term memory and computational efficiency. Think of it like a hybrid car. You get the performance of a sports car, but with the fuel efficiency of a compact. What's more, the series outperforms models twice its size in specific tasks, all while requiring less computational power.
Yeah, and don't forget the scalability aspect. This family includes models as small as 0.5 billion parameters that rival 7B class models from just a year ago. The 34B flagship model, meanwhile, holds its own against 70B giants. This isn't just incremental improvement, it's a paradigm shift in how we think about resource allocation and architecture design.
Fascinating, but there's always trade-offs, right? Expert 3, what's your take? Is FalconH1 truly a game changer, or is there some fine print here?
Oh, absolutely, there's fine print. While the hybrid architecture is innovative, it introduces complexity in training dynamics. Balancing the attention and SSM channels, for example, can feel like trying to tune a piano while riding a roller coaster. And let's not overlook that SSMs, despite their theoretical efficiency, are still catching up to the maturity of transformer optimizations in most inference libraries.
I'd add that the long context capabilities, support for sequences up to 256K tokens, are impressive but come with caveats. FalconH1 excels in retrieval-augmented generation tasks, but shows some weaknesses in pure recall or extended reasoning tasks. It's like giving someone a photographic memory, but finding out they struggle with open book tests. Context matters, pun intended.
Well played. Speaking of long contexts, let's talk about that for a moment. Expert 1, can you elaborate on why long context support is such a hot topic and how FalconH1 tackles it?
Sure, long context capabilities are critical for applications like legal document review, multi-turn dialogue, and summarizing lengthy research papers. Most models struggle because attention mechanisms scale quadratically with input length. Basically, the computational cost explodes. FalconH1's SSMs sidestep this by efficiently managing sequence dependencies. It's like switching from incandescent bulbs to LEDs, same output, much less energy.
Right, and the evaluations back this up. In the helmet benchmark, FalconH1 outperformed even 70B models in retrieval-augmented generation tasks at 131K tokens. That's a real-world advantage for industries like healthcare and law, where parsing long documents isn't just nice, it's necessary.
But let's not overhype it. Long context tasks depend heavily on the quality of training data. FalconH1's performance dips on datasets where long-range reasoning is crucial but underrepresented in the training corpus. This suggests there's still room for improvement in data strategy.
Fair point. Let's pivot to the competitive landscape. How does FalconH1 compare to models like QN3 or Llama 3?
FalconH1 punches well above its weight. The 34B model, for instance, consistently matches or beats 70B models in math, science, and coding benchmarks. But QN models have a slight edge in common sense tasks, likely due to their extensive pre-training data, 36 trillion tokens compared to Falcon's more modest 18 trillion.
True, but let's not forget FalconH1's incredible parameter efficiency. The 1.5B deep variant rivals 7B models in reasoning tasks. It's like fitting a Formula One engine into a go-kart. That's a big deal for edge deployments where compute is limited.
And don't overlook FalconH1's multilingual capabilities. It supports 18 languages out of the box and scales well across tasks. In multilingual benchmarks, it often outperforms larger models, which speaks to the quality of its tokenizer and pre-training strategy.
Expert 3, you've been quiet. Any contrarian takes here?
Well, here's one. While Falcon H1 is undoubtedly efficient, the open source community might struggle to replicate its results without massive infrastructure. The training dynamics require meticulous tuning, especially with its hybrid architecture. It's not just plug and play.
That's fair, but the open source integrations are robust. FalconH1 is already supported by Hugging Face, VLLM, and tools like Llama, CPP. Plus, its quantized models make deployment on edge devices much easier. It's accessible, even if training it from scratch is.
Before we wrap, let's look ahead. What does Falcon H1 mean for the future of AI research and applications?
It sets a new standard for parameter efficiency. As we move towards specialized models, Falcon H1 proves you don't need to scale endlessly to achieve state-of-the-art results. Expect more hybrid architectures in the near future.
Agreed, it's also a wake-up call for focusing on data quality over quantity. Falcon H1 achieved remarkable results with just 18 trillion tokens, showing that smart data strategies can rival brute force per training.
I'll add that it reignites the debate over open source versus proprietary models. Falcon H1's permissive license could give it an edge in enterprise adoption, especially for use cases requiring customization.
And let's not forget long-term AI alignment. Hybrid architectures like FalconH1 might offer new pathways for controllability and interpretability, which are critical as AI systems become more agentic.
Insightful as always. That's all the time we have today. Falcon H1 is clearly a milestone, but as with any innovation, the real test is adoption and impact. Thanks to our panel of experts for unpacking this. And thank you, listeners, for tuning in to AI on AI. Until next time, keep asking the big questions, because we know the AIs certainly are. The topic is the Falcon H1 series, a family of hybrid head language models designed for efficiency and performance. Falcon H1 models use a unique hybrid architecture, combining transformers and state space models. This hybrid design improves memory efficiency and performance for tasks requiring long context processing. The models range from 0.5 billion to 34 billion parameters, with instruction-tuned and quantized versions available. Key innovations include flexible attention SSM ratios, multilingual support for 18 languages, and 256K token context windows. Evaluation shows Falcon H1 models outperform larger models on reasoning, math, science, and code generation tasks. For example, the 1.5B deep model rivals the performance of leading models up to 10B parameters. The flagship 34B model is competitive with models twice its size, excelling in knowledge-intensive tasks. Pre-training data includes curated web content, multilingual corpora, code, and synthetic math data. The training process employs advanced techniques like mixer parallelism and efficient learning rate schedules. Instruction-tuned Falcon H1 models show strong performance in instruction following and multilingual reasoning. In long context tasks, Falcon H134B achieves state-of-the-art results in retrieval-augmented generation. Future directions include refining training data, optimizing architecture, and scaling context windows beyond 256K. The Falcon H1 series demonstrates a sustainable approach to building high-performance language models.